Okay, well, we're very happy to have Surjeet Rajendran all the way from Berkeley. He's going to tell us about firewalls in general relativity.
Right. Thank you very much for inviting me. It's always fun to be here in Davis. I noticed there's actually a small typo in my title slide. It's actually supposed to be this. Anyway, so everyone knows about the black hole information problem. So I'm not going to start by talking about that. I'm going to instead discuss a problem that is true in a closely related geometry, but it's something much less appreciated, which is the problem of what are called Cauchy horizons in Reissner-Nordstrom and Kerr black holes. Pretty much everything I say today will be true only for the Reissner-Nordstrom solution in terms of the actual work we did. But the problem, of course, exists in the Kerr geometry also. And I strongly suspect that the kind of technologies that we talk about today will probably be also true for the Kerr geometry, although we haven't actually shown it. So we'll mostly entirely focus on the Reissner-Nordstrom case. And so if I look at the Reissner-Nordstrom black hole, its geometry is like so, right? And famously, it has two horizons, an inner and outer horizon. Let's say R1 is the inner horizon and R2 is the outer horizon. And if it's a big black hole with a big mass and a big charge, the inner and the outer horizons, they exist in a region of low curvature, so you must trust general relativity. So what does the causal structure of this black hole look like? I'll first just show a normal person diagram before I show the Penrose diagram version of this. But if I just simply draw the coordinates, okay, just simply the R coordinate and ask what happens to someone who falls into this black hole, this is basically what would be true if this geometry was completely correct, right? That you really trusted the GR solution. So because you have an inner and outer horizon, the following is true. This quantity f of r, say it's positive when you're outside the outer horizon. It's negative in the region between the outer and the inner horizon. And it is positive again once you're inside the inner horizon. And that means if you're someone falling in, outside over here you can move back and forth in r, no one cares. But the moment you're inside the outer horizon, you have no option but to keep falling towards the inner horizon. And let's say you go inside the inner horizon. Once you're inside the inner horizon, time and space are normal again, so you can avoid, for example, the singularity. The singularity is now a point in space. So you can forever try to live in a region of low curvature, where if you trust this metric, GR should continue holding. And if that is the case, something interesting can happen to you. You can basically ask, what happens if I try to leave that region where the inner horizon exists? Where can you go? That is the question. Obviously, you can't go where you came from, because that would require you to go back in time. Right? So that doesn't make any sense. So in the standard GR story, what you would say is that if I draw the Penrose diagram, what I'm going to do is I'm going to try to extend that region, okay, to a different universe. So in this picture, you're falling in. There's the outer horizon. You go through the point r equal to r1, the inner horizon, if you will. And now you're trying to leave it. Okay? As you try to leave it, you can't go back to the original space-time. That requires you to go back in time. So you extend your space-time to a different universe. But which universe? GR doesn't say. And indeed, whatever other universe you're going into will have a different set of boundary conditions. So what this looks like is that from the point of view of general relativity, the moment you have such a Reissner-Nordstrom solution, you have a failure of predictability. I can't tell you what happens to this guy because he ends up in some random universe somewhere. Okay? And that is a problem. It's a problem of the fact that the Cauchy horizon cannot be solved. The Cauchy problem cannot be solved in GR anymore. So the only way to avoid this problem really is if there is a sufficiently large change to the metric here, so that the inner horizon no longer exists. And if you have a static black hole, okay, something that is not changing in time or whatever anymore, the only sensible possibility there, if you want to remove the inner horizon completely, is for there to be something singular happening at the inner horizon itself. And that's actually a region of low curvature naively in gravity, but yet if that solution was something that you trusted, you have a problem of predictability, and the only way to get out of it is by making something singular there. Not only that, this also has to be a fast classical effect. There is no quantum black hole evaporation, entanglement, nothing happening. The moment this black hole forms, if this solution is correct, you have this problem. Okay? So the people in the GR community are well aware of this problem. And there's an old idea on how to solve it, and that is an idea due to Werner Israel and Eric Poisson back in the 1980s. This is a phenomenon of what is called mass inflation. And their basic point is the following. Suppose I actually form this geometry. Okay, I've got an inner horizon and an outer horizon, and I'm going to have let's say, some external photon or whatever fall in from far away. And let's say I have an observer somewhere inside the inner horizon sitting somewhere in here watching what happens to this photon. What I'm going to see is that the energy of this photon gets dramatically blue shifted as I fall towards this black hole, as I go towards the inner horizon. It kind of blows up like this as R1 over R minus R1. So naively what you therefore think is that, well, as this energy falls in, a small energy here gets dramatically amplified in here, and potentially that could give rise to a large back reaction, changing this metric. Okay? So this is the word instability that you'll often hear thrown about in this particular context. So I'm not going to disagree with the fact that there is going to be something singular happening in here, but I do have some comments about whether or not it's really external perturbations that can do this trick. Right? So, but the main point is that because of the fact that the inner horizon has this blue shift feature, the key thing is that if you notice, as this guy falls in, you can potentially accumulate a lot of mass in here locally without changing external parameters, basically because the blue shift has taken care of the large increase in the mass as it falls in. Okay? So that will be an important point that I will continue using, but my concern is basically, is it really the case that it's external perturbations that is going to come and destroy the solutions of this black hole? And there are two versions of this complaint. One is to basically ask something quantitative, right? We don't really believe in infinities in physics. We don't really know how anything should fall, for example, at distances shorter than a Planck length. So if that is the case, whatever energy is falling in, I can try to regulate that divergence by basically saying, look, I don't trust GR description of how something should move at a distance shorter than a Planck length. And that basically means I will regulate the singularity. Okay, it's no longer an infinity out there when R goes to R1. And that means when something falls in, I will get an amplified but finite response to how much mass can build in. And the answer is something like E infinity, which is the energy far away, times m over n Planck. So that's like a large amplification factor of the energy that falls in, but nevertheless something finite. And so if you now do something very naive and ask, well, if I really want to have, let's say, a singular region out there, which is what the GR guys want to have, it must have some density of m Planck cubed, that's where GR should be cut off. How much mass should naively live in that shell? Well, the amount of mass is something like m Planck cubed times R1 squared, which is then order m squared over m Planck. And so what that tells you is that if you really believe this perturbation story, you have to put in a substantial amount of mass, something order the mass of the black hole, in order to quantitatively explain how this singularity could really exist. Not only that, recently people have thought about how a positive cosmological constant could change this particular story. And naively, that should be surprising to you. Why should a positive cosmological constant change anything at all? Because after all, some crazy thing about the interior of the black hole, a positive CC shouldn't have any effect. But people like Peter Hines have shown that if you have a positive cosmological constant, the blue shift that this guy acquires as it falls in gets somewhat ameliorated by the fact that there's a redshift in this thing falling in from far away because of the expanding universe. Okay? But again, right, it makes no sense that a positive cosmological constant, which is some statement about the exterior, is going to dramatically alter some statement about the interior. Okay? So I am skeptical that it is external perturbations that is actually going to be responsible for creating this large mass buildup over there. So one should ask, what is it about the inner horizon that makes this possibility? Why is there this large blue shift in that particular region? And that is due to an interesting fact about the interior geometry of the Reissner-Nordstrom black hole, which is that the gravitational singularity itself is gravitationally repulsive. Okay? So when you are outside the inner horizon, gravity is attractive, things keep falling in. But as you go inside, gravity is effectively a repulsive singularity. Okay? And in the Reissner-Nordstrom case, that is because of the fact that you have charge, and there is therefore an electromagnetic field, and the electromagnetic field has a large stress tensor in there, and that stress tensor effectively has pressure, which pushes you outward. In the case of the Kerr black hole, this is because of the fact that the Kerr black hole has rotation, and there is therefore vorticity in the metric, and that centrifugal force pushes you outward. Okay? And that's effectively why you even have the inner horizon, is basically because gravity itself somehow is being cancelled out here, right? Due to the fact that it's repulsive on this side and attractive on that side. And that picture tells you that just because I, similarly to how I had an external perturbation get blue shifted from this side, I can potentially also, for example, take the singularity and kick some mass on this side, and as I kick that mass on that side, that mass will also get blue shifted as it goes over there, right? Because there's a repulsive force pushing you outward, which should also give rise to blue shifts. So this tells you there's an interesting fact, which is the fact that I can potentially take the mass of the singularity and say kick some of it outward, and that could give rise to a large blue shift as this mass goes over there, giving rise potentially to a significant buildup of local density without changing the external parameters of the black hole. Right? So I could have large internal mass density sitting in there without changing anything external about the black hole. And of course, it's only the external parameters of the black hole that we know something about. And what that means, of course, is that once you realize the same magic that you need to happen for the case of the inner horizon of the Reissner-Nordstrom black hole, the moment you realize that's possible simply from internal dynamics of singularity, you could then try to patch that same picture onto, say, a Schwarzschild black hole as well, where of course you don't change the external geometry, but maybe you can change the interior in some way so that you are allowed to do something like this, creating singularities in regions that you don't otherwise suspect. Okay, that's the overall picture. So let me give you a more detailed outline of what we did and the mathematics and what we did. So I was, told, and I learned in this country when I came here, that there's a good way to organize knowledge, and that is in this following sense. So I'll first start off with the known knowns, and the known knowns are, of course, the solutions that we found in GR. Okay, so these are things you can't argue about. You can go and compute and say and see what we did is right. So that'll be the mathematical solutions of what we did. Then there are the known unknowns, and this has to do with the specific story about the formation. Okay, we don't have a detailed theory that tells you how this thing is formed. We have plausibility arguments, and you can choose to buy them or not buy them. But anyway, it's just a plausibility argument. Then there are some things that I like to call unknown unknowns, and this has to do with the fact that the specific kinds of technology we use to create our solutions can potentially also be used to create negative mass Schwarzschild solutions. And it's unclear if you really form them in our case, and it's also unclear if they're really problematic. So anyway, I'll just tell you what the story there is. And in physics, it turns out there is one more point of knowledge, which is the point of an unknown known. And that is the fact that I don't know how this solution forms, for example. I don't know its detailed properties in many ways, but I can experimentally try to think about ways to go and look for it. Okay, so experimental signatures of the unknown knowns. So let's talk about the solutions that we actually found. Okay, and let me start off first by describing the inner horizon of a Reissner-Nordstrom black hole, or what we think actually happens. So here is what we want to do, right? We want to replace the inner horizon of a Reissner-Nordstrom black hole with something singular, the singular shell, so that the external mass and charge are what we observe. Okay, so I want to have a lot of mass internally, but a very small mass outside. How are we going to do this? So what we're going to do is we're going to take the exterior metric to be the required external Reissner-Nordstrom metric. Okay, so that exterior metric, for example, is described by an inner horizon, which the parameters are a little bit funny. So the term R1O, it refers to the inner horizon, that is the R1, O being the outer metric. Okay, so there's a bad nomenclature here. Hopefully I don't confuse myself and you don't get confused. But R1O refers to the inner horizon of the Reissner-Nordstrom metric of the black hole that I want. Okay, the one outside. And so that guy has this inner horizon there. And what I want to do is I want to place a shell, okay, a time-like shell, just a physical shell, a short distance away from that inner horizon. And I basically want to ask, what does it take for that shell to be singular? And by singular, I mean have a Planckian density. Obviously, if this is all there was, that wouldn't work because the external mass would be wrong. So what I'm going to do is I'm going to replace the interior metric, which we have no idea what it is, right? Because all we know are just external parameters of the black hole. I'm going to replace the interior of the metric with a different internal Reissner-Nordstrom metric. And I'm going to choose its parameters to be free. In particular, I will take its charge to be very different from the charge of the external black hole. And so all that means is the fact that the charge here is very big, and I'm going to place a shell over here. The shell will have exactly the charge it needs to have so that the external charge is correct. Okay? And I'm also going to allow the mass of that black hole to be whatever. To be whatever it needs to be to do these things. And then I'm going to use the Israel junction conditions to match this internal metric with the required external metric. And I want to ask, is that actually possible? And the question is, can you do this match by using reasonable matter? And my metric for reasonable matter is that it has positive energy densities. It satisfies the dominant energy condition, something like that. Okay? Because obviously, if I could only do this match by having negative mass, that would be stupid, because there are instabilities. What would be interesting is basically such a match can be made with all the densities being positive. How do we do that? It's a pretty straightforward exercise. you essentially have two metrics, G in and G out. G in is the interior Reissner-Nordstrom solution, which only exists in this side over here. And it's parameterized by its own inner and outer horizons, okay, R1I and R2I. These have nothing to do with the external parameters, right? This is just an internal metric completely. And then there's an external metric, which is this guy, which has its inner and outer horizon, and these are the ones that we physically observe outside. Okay. To do this matching, the Israel junction conditions require that the induced metric is continuous along the shell itself, and so we basically have to reparameterize the time coordinate inside the interior, okay, so that the matching can actually happen, and all of that is pretty standard, straightforward stuff. So that's it. You just take these two metrics, you run the Israel junction conditions, and you ask, what does it take for me to place the shell, okay, at a point, let's say R0, which is just inside the inner horizon, and ask the following questions. You can basically ask, well, suppose I want this shell to be truly singular, okay? I want the shell to have M-Planck density. What do the parameters of the interior black hole have to be? Okay, what are R1I and R2I, so that I get a singular shell over here? And then you can ask questions like, is the charge to mass ratio reasonable? Is something truly crazy going on over there?
So just to be clear, you're requiring the shell to exist just outside the inner horizon?
Just inside the inner horizon.
Because I think you misspoke at one point and said,
oh, sorry, yeah.
You meant inner. Okay.
Yeah. Okay. So here's the matching then. We take R0 to be the inner horizon R10 of the external black hole times 1 minus epsilon. I'm going to ask what happens when I want to do this matching. The limit epsilon goes to 0. Okay. The limit epsilon goes to 0. The density is a finite quantity. It is that particular thing. And the pressure is actually something that is divergent with epsilon. As epsilon goes to 0, the pressure actually diverges. It is this particular thing. And now we do something physical. We're basically going to require that I want to place the shell at a physical Planck distance away from the inner horizon. Okay, that's physically what I want to do. When I demand that, something interesting automatically happens. At the moment I place the shell just a Planck length from the physical Planck length away from the inner horizon, the pressure of the shell becomes Planckian. It's negative M Planck cube. And then the only question is basically, what are the parameters of the inner horizon, what are the parameters of the interior metric? Okay, R1I and R2I, so those represent the internal Reissner-Nordstrom geometry. What do those parameters have to be for me to get a Planckian density as well? A positive Planckian density out there. Okay, so there are a couple of possibilities of what R1I and R2I can be. I like this one because the other one more easily gives rise to negative mass Schwarzschild solutions. I'll comment on that later. But for now, let's just simply say that R1I and R2I, which are simply parameters that talk about the interior Reissner-Nordstrom geometry, let's say we take them to be order M Planck R1 squared. Okay, these are free parameters after all. There's nothing that we physically measure. So I take these parameters, and automatically the density also becomes M Planck cube.
This is independent of the amount of charge that you have left in the singularity?
Yeah. Because it's like, they're not fine-tuned or anything. They're just simply parametric in this order. This is what you get.
Well, choosing R1 and R2 is choosing the charge.
Choosing R1, R1, R2O and R1O is like choosing the charge externally. But yes, it is a case that choosing R1I and R2I is also choosing the charge and the mass. But I'm just saying it's not a fine-tuned choice. It's like a fairly broad range of possibilities where it works.
You're basically assuming that the charge left inside is parametrically small compared to the total charge.
Yeah.
That's why it drops down.
Yeah. Okay. So, this is just a simple exercise. You can put the shell and take these parameters and ask what the density and pressure have to be. And let's ask what the characteristics of the solution are. Okay, so that's what we have. We have a shell that's a Planck length from this with these parameters.
So physical distance, you mean proper distance?
Yeah. So when this happens, something interesting automatically happens, and this is not something that you put in my hand, right? So when I take the shell and make it Planckian in density and pressure, and just a Planck length away from this, from the inner horizon, right? It turns out that the physical distance from this shell to the singularity here at r equal to 0, the physical distance also becomes order 1 over m Planck. Okay, it's a Planck length away. Not only that, if you compute the Riemann invariant, let's say r mu nu lambda sigma squared, that is also Planckian for all r less than r1f. Okay, And what that means is that in this particular solution, there's a complete breakdown of general relativity just inside the inner horizon. Okay? Which is basically what you want in order to solve the Cauchy horizon problem. This is something calculable and verifiable. And you can ask, why should I trust this solution, right? After all, this is a solution where GR is broken down in this crazy way in the interior. Why should I trust any of the things that you're saying? The reason why I can sort of trust it is basically because of the fact that I can take the solution as a limit of non-singular solutions. So basically, if I, for example, take this surface and don't put it a Planck length away, let me put it some parametric distance away, and let me not take R1I and R2Y to be this order of magnitude, let me make them smaller. So if I made them smaller, this shell would not be Planckian, GR would not break down in this dramatic way, okay? And then you would trust everything that I'm saying, but then you take the limit, and then you see, the limit approaches this particular thing.
How does the Kretschmann invariant, the curvature squared, behave as a function of distance as you move out from this shell?
So as you go outside, it is exactly the Reissner-Nordstrom case. Right, because just outside the shell, the metric is exactly Reissner-Nordstrom, the standard Reissner-Nordstrom story.
Right.
And just inside is very different. So when you go outside, it'll just go back to what you normally expect it to be.
So then the gradient...
Yeah, there'll be some large gradients there, yes.
Some,
Big thing, yeah.
okay.
Yeah, there's a shell there, right? There's a shell with Planckian density out there.
Yeah.
Yeah.
Okay.
Yeah. So what I find very interesting about the solution is basically that if I ask physically what is the local mass of the shell, and in fact even the mass of the singularity which I require in order to make this whole solution work, is that the local mass is basically order m squared over m Planck. Okay, it's enormous mass inside, and except the ADM mass, the mass that you will see outside of this black hole, is just order m. So it's parametrically larger than what the external parameters are. And of course, all of this is not due to any external perturbation falling in. Because I'll point out that even in the external perturbation case, if you wanted to solve this problem, you did require a buildup of mass that is order m squared over m Planck, quantitatively. But here you just see that the same thing is possible simply from what I would like to call internal singular dynamics, which is basically the statement that the singularity itself is able to share its mass and charge so that it's able to patch on to a low curvature region out here, even though the curvature inside is tremendously big. Okay? And I was very surprised to find such a solution. I would not have thought such a thing was even possible. So let's ask, is there something weird about the charge to mass ratio? Maybe I require something crazy about the charge. So you can, given R1I and R2I, as you pointed out, I'm indeed picking a mass and charge for the black hole. When you take these parameters to be what they are, the charge is something like this. So you can then compute the charge to mass ratio in Planck units, and that's a quantity that turns out to be something of this form. And the only thing that's interesting about it really is the fact that since R1I and R2I is much bigger than R10, right? This quantity is essentially some order 1 number, okay? Because this one, the denominator is basically the same thing as the numerator, except of course it's strictly bigger than 1 because of the fact that this is inequality. This is subtraction, yes.
So, if you use you're using an infinitely thin shell, right? Which
Yeah.
is why you're able to solve this by just some junction conditions.
Yeah.
So the thin shell approximation assumes that the forces that are preventing this brain or membrane or whatever it is from blowing up are much larger than the other forces around,
Right.
But so you could wonder whether if you tried to smear this thing out to be Planckian thickness rather than the shell to be Planckian thickness, whether you would really still be able to get these solutions.
Yeah, I mean, I would say that, once again, thinking about it from the perspective of not quite being singular yet, but just being sub-Planckian, right? There, I don't see any particular reason why this analysis would fail. So there, indeed, is the case that I can, for example, think of a Planckian thickness or whatever, but everything else is sub-Planckian. So I don't see a problem there. And of course, this charge to mass ratio is bigger than 1, but doesn't really bother me, because when you compute that with a proton, that's like 10 to the 19. Right? So this is basically a statement that this shell, for example, could be made out of 10 to the 19 neutrons and 1 proton. Nothing particularly weird about it just yet. The one thing we did check is basically asking, well, how important is the full construction? So could you, for example, just have the shell by itself without the inner singularity? Okay, and the answer to that is no. There is no time-independent solution. So if I take this shell with this mass, this big of a mass and this big of a charge, that shell does not want to stay there. It's not a static solution. It wants to blow up, or something weird would happen to it. Okay, so it's indeed the case that I can do this matching and all of this thing can be static, only because the inner singularity, if you will, is binding energy lowers whatever energy is there in the system to make the whole thing exist as a static solution. Okay. Of course, I don't know anything about the microphysics of the shell. This is just some shell. All I know is just a stress tensor, right? I just know its pressure and its density. Any statement about stability is a statement about derivatives of the pressure or the density, and the GR thing that I've done so far doesn't tell you what the derivatives are. Okay, so all I can just say is like, look, isn't it kind of crazy and interesting that I can put the shell in there, and but you don't know anything at all if you're outside, right? The external geometry is still very much a vanilla Reissner-Nordstrom, but the interior is dramatically different. So I'm going to basically see how these same ideas can also be used to create a firewall or a singular density outside the event horizon of a Schwarzschild black hole. The technology is something very similar. We're going to take the exterior metric to be external Schwarzschild metric. That's a Schwarzschild metric that we want. And I want to place this shell just outside the event horizon of that Schwarzschild black hole. Okay? And I'm going to ask, what does it take for that shell to be singular? Okay, to have Planck density. And indeed, to make any of this work, what I'm going to do is I'm going to replace the interior of the black hole, okay, by a Reissner-Nordstrom black hole, okay, which has a much different mass and charge than what is there outside. And the shell will, of course, have exactly the opposite charge, so that I end up getting the Schwarzschild black hole outside. Okay. And once again, I'm going to use the junction conditions to do this matching, and we can ask, is such a match possible with positive mass and reasonable mass? So the same story as before. The interior metric is this Reissner-Nordstrom metric with a very big R1 and R2. The inner and the outer horizon of the interior metric. They're just like parameters of the solution, if you will. And I'm going to match that on to the Schwarzschild metric outside. Okay, parameterized by RS. And I'm going to do this matching at the point R equal to R0, which is slightly outside the event horizon of a Schwarzschild black hole. And what I'm basically going to be asking is, what do the values of the interior metric have to be, its mass and charge, so that I'm going to get a singular shell just outside the Schwarzschild horizon? And what is the charge of the shell? Is there some funny charge to mass ratio? Okay. So, same technology as before. Take R0 to be Rs times 1 plus epsilon, and consider what happens to the story. The limit epsilon goes to 0. The density is some finite quantity. The pressure diverges as 1 over epsilon, so 1 over square root of epsilon. And once again, what I want to do is I want to regulate that divergence by placing this shell at a physical distance that is a Planck length away from the Schwarzschild radius. And once you do that, it turns out the pressure automatically becomes Planckian. The only difference from the previous case is that the pressure here is positive, though the pressure was negative. And once again, I'm going to ask, what does it take for the density of the shell also to be Planckian? And once again, I take R1 and R2 to be comparable, okay, to m Planck Rs squared. That's the branch of solution I'll choose, and that gives you Planck density as well. So if you look at the shell, the characteristics of the shell are very similar to the kinds of shell that I needed for the Reissner-Nordstrom case. Okay, and that to me is interesting because in the case of the Reissner-Nordstrom case, there is no black hole evaporation, Hawking radiation, none of that stuff. There's a plausible way to solve that problem, and shells of a very similar sort also seem to be what you would need to get a firewall at the black hole event horizon as well. Okay. Let's ask some more physical characteristics of what actually happens. So once again, in this case, if I compute the Riemann invariant, R mu nu lambda sigma squared, it is the case. Yes.
Sorry, just another question: is the tension of the brain or whatever it is it Planckian or is it bigger than Planckian?
The density is Planckian.
So the tension there is also the
Pressure.
The pressure is also Planckian.
So the pressure is the tension.
Yeah.
Yeah.
Yeah. Okay. So once again, the Riemann invariant also blows up. It's order m Planck to the 4th, just inside the Schwarzschild radius over here. Okay. So once again, this is a solution where it's the same Schwarzschild geometry outside, but just in the interior, GR is completely broken down. Okay. And remember, in this particular case, the interior of a black hole is not the standard Schwarzschild interior. It's this Reissner-Nordstrom interior. So the singularity is again a physical point. It's a point in space at r equal to 0. So once again, it is a case that the physical length from the shell to the point at r equal to 0 also turns out to be order 1 over m Planck. And mind you, this is not something that we put artificially, right? It's a characteristic of the solution. The moment you choose these parameters, this is automatically true. And what I like about this somehow is basically that this gives you a physical understanding for why the black hole entropy could scale with the area. Okay? It does require some assumptions on my side, but what you really see is the fact that this is a very interesting solution where the area of the shell is the same thing as a standard Schwarzschild black hole, right? It would scale as RS squared, the standard Schwarzschild area, but the interior is just a Planck length away. It's a Planck thickness. So this is an object with a big area but a very, very small interior. Okay, so the physical volume scales with the area, right? And so if you, for example, thought that the inner singularity was a very simple object with just a mass and a charge with not a whole lot of entropy sitting in there, then the reason why the black hole entropy would scale like the area is basically because all of the entropy lives on the shell over there. Okay? So of course this doesn't have to be true. The inner singularity could be much more complicated, but at least to me it is interesting that this feature exists in the solution, not by something that I put in by hand. It just automatically happens to be true once I wanted to have some other desired properties. So at this point, all I've really shown is that this is a new kind of naked singularity in GR, right? Like I'm basically telling you that the exterior here is Schwarzschild, the interior is something totally different, and there's a singularity right outside the Schwarzschild horizon. Okay, you'd be like, okay, great. How do you form it? Right, that's a real question. Question of formation. And this is something that, of course, is a problem in many other contexts in other attempts to, for example, solve the black hole information problem, things like fuzzballs and gravastars, things of that sort. And the problem can be couched in a very simple way. It's a statement that if I take a sufficiently large, low-density cloud of matter, that matter can collapse to form a black hole. And it's indeed the case that the fuzzball and the gravastar, things of the sort, these are naked singularities, or, well, they're just sort of solutions without a horizon. So the question you have to ask is basically, well, I have this low density gas that's collapsing, it becomes singular or whatever. How does that become either the fuzzball or the gravastar, right? It's very hard to do, very hard to see how that's possible in the case of the fuzzballs or the gravastars because of the fact that these are low density objects. And if they're low density objects, you expect GR to dictate how they're supposed to move. So it's unclear how you ever form them because GR would say, look, I'm obeying all the standard rules of general relativity. Singularity theorems tell me that the moment I have this thing inside the inner horizon, there is no hope for me except to go and form into a black hole, right? So the formation story does not exist for these two cases. How am I any better? Am I even any better? So my only hope here is that there's the key distinction between a low density solution such as a fuzzball or a gravastar from the singular shells that I'm talking about, because the local motion of a singular shell is not subject to the causal structure of just general relativity alone. Okay? And here's what I mean by this. Imagine that I take my singular shell and I'm modeling the bits on top of it by some scalar field. And the scalar field I can write down a standard nice looking Lorentz invariant theory that describes its motion. Okay? So it's got like a equivalence principle preserving coupling to the metric G mu nu, d mu phi, d nu phi. Okay? And it very reasonably also has couplings to higher dimension operators, R mu nu, m Planck squared, so on and so forth. So these are Lorentz preserving but equivalence principle violating couplings that can and probably do exist for pretty much any field that you write down. Usually these terms don't matter, they're too small. And when they're too small, the causal motion of the shell will be dictated entirely by the GR metric. Okay? But in my specific solutions, if you notice, these are specific solutions where things are singular, which means this parameter is actually big. And when that parameter is actually big, the effective metric that this guy will see, okay, will be different from that of GR. Because I don't have a theory for what that metric is and all of that stuff. Okay, so this is just a plausibility story for how such a shell could evolve in a Lorentz preserving theory, but in a way that violates causality dictated by general relativity. Okay, so in my view, I think it's very reasonable, and doesn't mean it's true, but plausible that there could be causal but GR violating evolution of the shell. So how do I imagine this thing actually forming from low density matter? Right, I take a low density cloud of matter, and this matter starts collapsing. Okay. As it starts collapsing, the matter will at some point form a singularity. It becomes something dense and big at Planckian density. And when that is the case, singular dynamics can of course cause a charge separation, for example over here, positive charge and negative charge, and making each of these things singular, very, very singular. And then the whole point is that that shell can now move outward and go towards the Schwarzschild horizon, simply because this particular dynamics that allows it to go over there is not dictated by GR alone. Right? It can have this acausal motion, even though it is coming from a Lorentz preserving theory. You can ask, yes, sir.
Do you have an estimate for what the time scale would be for when the firewall kind of reaches the inner horizon?
I don't, because I need to know the theory, right? So you can at this point very reasonably ask, where's the proof, right? This is a part of the story where to answer any of these kinds of questions, I would have to know what the theory really is, right? So you can very reasonably say, there's no proof, there's no collusion, right? But something of this sort needs to actually happen, okay? I can't prove it, okay? But the thing, okay, is that about collusion is that collusion is very hard to prove, but sometimes you suspect it could be true, okay? And that is pretty much all I have to say about the formation. It's just a plausibility argument for why such a thing could be true. But you can ask, what could be more? The more reasonable thing to ask is basically, look, I have certain properties about the world that I like, and what should the UV be so that I can have this particular kind of evolution that I want to have, but maybe preserve other properties. And so the kind of properties that the UV should be, whatever the UV theory of gravity or whatever it is, okay? My main point here is the fact that in this kind of solution, this kind of picture, the UV is relevant. Right? So this is something that's interesting to me in the sense that in any other possible attempt that has been made to understand the black hole information problem, it has been very unclear why the UV would ever matter. In this case, there's a plausible path in the UV where such a thing could actually be true. And so what needs to be true in the UV is that whatever dynamics you actually have should allow this kind of singular evolution for these very specific kinds of objects. Okay, these very high density, Planckian density things should be allowed to move along space-like paths. Space-like in the sense that the GR metric would claim it's a space-like path, even though that actually could potentially come from a Lorentz-invariant theory in the ultraviolet. And it must also be the case that this cancellation that happened over here, where basically I've got this dramatic change, right? In the interior, the mass is m squared over m Planck, but in the exterior, the mass is just order m. And it must be the case that the binding energies or whatever sitting in this case must have this miraculous cancellation over here, and the UV should have that aspect of the story. I have no idea what the UV is, so this may not even be true, but all I can say is that such a cancellation is plausible simply because there's a solution in GR that you can match onto, right? So it's already to me very interesting that if I take the Schwarzschild horizon and I put a shell right outside of it, the fact that there is this crazy solution where I have dramatically different interior masses and curvatures than what I would have normally assumed, while the exterior is something very vanilla. So, okay, that exists in GR. Could the UV match onto that? I don't know. The additional reason why you might think such a thing is possible, of course, is because you require such a similar cancellation to exist in the interior of the Reissner-Nordstrom black hole. There is no other possibility out there. Okay, and of course, to some extent, the formation story of such a shell in the Reissner-Nordstrom case is a lot easier because it's not like you need to have some shell that moves along some space-like path. Okay, the shell evolution simply could happen along a time-like trajectory. So, for example, it's very reasonable that for whatever reason, in the case of the Reissner-Nordstrom black hole, the evolution of the shell could happen quickly because it just has to move over a time-like path, while maybe it's a lot harder for it to move along a space-like path. I don't know. You have to know what the theory is, but at least the fact that something similar like this has to happen gives me some optimism for why this could. So let me quickly tell you about the negative mass Schwarzschild solutions in our story and what we think about them. And here's the main point, right? Is that I have no idea what the microphysics of the shell or the core singularity are, right? I don't know what makes up these things. All I basically said was, look, I have this metric here, I have this metric there, I'm going to mass them together. And look, it's incredible to me that a positive density solution does the whole thing. So what's really going on, obviously, over here is that there is somehow a very delicate cancellation of the interior masses with the interior binding energies. Okay? It's not, strangely enough, a fine-tuned cancellation in the standard way. I didn't have to pick parameters very carefully. I just had to pick parameters to order something and this cancellation happened. But you might ask, well, is it possible that you do too much of cancellation? Right? If you do too much of a cancellation, you could then end up getting a solution that has negative mass outside, even though everything that went into it were objects that had positive density and pressure. And then you might say, well, if the kind of objects that you require for your black hole story, if those same objects can also be used to create negative mass Schwarzschild solutions, maybe you may suspect that the UV does not allow you to create such objects, right? Which would then invalidate what I'm saying, because, I mean, in a sense, part of my story is the belief in what the UV could do. All right. So let's ask if there's a difference in the kinds of objects one needs to form the positive mass solutions that I require, that I want, and the negative mass solutions that I don't want to have. Okay? And in a sense, that becomes a potential restriction on what the UV is in terms of what objects I'm allowed to play with. So we perform the same analysis. I'm going to have an interior Reissner-Nordstrom metric. I'm going to match on to an exterior negative mass Schwarzschild solution. That is just R replaced by R plus RS instead of R minus RS over there. And then I'm asking the same question, can I do this matching and then get a reasonable stress tensor, by which I mean a positive density solution with Planckian pressure and Planckian density and a reasonable charge to mass ratio. So the key difference between this matching and the matching we did in the case of the inner horizon of the Reissner-Nordstrom black hole and the Schwarzschild horizon is the fact that this parameter RS for the negative mass solution is simply a parameter. There's no horizon or anything over there. It just tells you this is the negative mass that you have. Okay? So you can basically think about doing this matching at any value of R0. There's no specific value you want to choose. Right? There's no motivated choice. You can simply ask, I'm going to do this matching wherever for whatever R0 out there, and can I get something strange actually happening? And I'm going to ask, what does it take for these parameters to get density and pressure to be m Planck cube? Okay? So the pressure of this particular quantity, it doesn't diverge anymore because there is no natural horizon or something in this geometry. So essentially what I'm going to do now is basically look at this object and say, look, the shell that I wanted, this brain that I wanted, had to have m Planck cube density. So I'm going to pick these solutions, pick the values of RS, R0, R2, and R1, make them whatever I need to make them in order to somehow make the pressure m Planck cube. What are the possible ranges out there? Okay. So if you stare at that for some time and you do some algebra, you convince yourself these are the three ways in which I can actually make this pressure m Planck cube. Okay. One is I can take R0 to be very small, less than 1 over m Planck. The other possibility is I could take R2 to be much bigger than R1. And the third is the kind of possibility that we talked about earlier, which is the solutions that I actually want, where R2 and R1 are comparable for the interior black hole, and take RS to be this particular object. So this one doesn't trouble me too much because if I take R0 less than 1 over m Planck, in this particular solution, if I compute the Riemann invariant, R mu lambda sigma squared, you'll find out that GR actually breaks well outside the shell itself. So it's kind of a dumb solution because since GR is already broken down, I don't trust that this thing actually exists. R2 much bigger than R1 is actually bad in the sense that if I construct the solution with R2 much bigger than R1, I'll find out that I have negative mass Schwarzschild solutions and I also have positive mass Schwarzschild solutions. And that's why I didn't choose it earlier. Right? Because then it turns out that when R2 is much bigger than R1, you don't really care about anything with the interior at all or what metric you're really matched onto. Okay? So that's why we don't choose it. Right? So basically say, if the singularity had objects of the form R2 much bigger than R1, you can create both positive and negative mass Schwarzschild solutions. But we didn't choose that one, okay? Because it's not useful. So the things that would be maximally bad are things where R2 and R1 are comparable to each other, because these are exactly the kinds of objects that we require in order to form our positive mass Schwarzschild solutions. Okay? So how bad are they? Indeed, when you take R2 and R1 comparable and make these parameters, RS is just a free parameter, take it to be that, you will indeed get solutions with the density and pressure are m Planck cube. But here's the main point, right? Whatever UV theory is, I don't know what UV theory we have in the world, but whatever UV theory is, doesn't just tell you some random density and pressure, there's probably some specific equation of state. Right? So we can, for example, choose pressure to be 1/4 rho, okay, just as an equation of state for the shell in the UV. And then you can ask, with R2 and R1 being comparable to each other, what do we need in terms of the other parameters in order to construct the positive mass solutions that we want and the negative mass Schwarzschild solutions we don't want? And then they can test for the breakdown of GR, which is a statement that when does the Riemann invariant blow up. And it is a case that is not parametric, but numerically and strictly numerically true, that if I, for example, take this density pressure to be 1/4 rho, and anyway, there's an open set around it, it's not like I specifically as 1/4 rho or something around there, then for the positive mass Schwarzschild solutions, the Riemann invariant actually blows up a little bit inside R less than RS. So the breakdown of GR happens inside the shell. So that's something you're okay with. Okay? While for the negative mass Schwarzschild solution, the breakdown of GR occurs outside the shell. This is not parametric, but it's a strict numerical inequality. Okay? So in that sense, you would say, okay, I trust this stuff more than I trust that one. Just out of curiosity, one can ask, even though we can actually avoid these negative mass Schwarzschild solutions by this kind of choice, the pressure being 1/4 rho or something around that, one can really ask how problematic is it really? Okay, what's the big deal? So here's the reason why one might consider this problematic, is basically because, of course, normal matter, which has positive density, is not going, and positive mass is not going to collapse and form a negative mass solution, because we are preserving the ADM mass in the entire story. The reason why you worry about this is basically spontaneous vacuum decay, right? You can basically have a positive mass black hole and a negative mass black hole pop out of the vacuum, and they both move in the same direction, which then conserves both energy and momentum. And the problem with such a process is basically that this process probably has a very, very small matrix element. Okay, it's exponentially suppressed, creating this crazy classical solution, whatever. But the problem is, no matter how small the matrix element is, the rate for this process is multiplied by a phase space. And the real issue is the fact that the phase space, if you believe that this story that is in a Lorentz invariant theory, this phase space is non-compact, because the Lorentz group is non-compact. And that essentially tells you that this rate, no matter how small the matrix element is always infinity. The physical understanding being that this process can occur in every rest frame. Right? In every rest frame, it may well be the case that the rate for this is very small, but it can happen in every rest frame, and that means I can integrate over all of phase space, all of the rest frames, which then gives me an infinity, simply because the Lorentz group, I can do arbitrary boosts. Okay? So, and furthermore, there's no way to regulate this divergence in a Lorentz invariant way, because that would basically correspond to picking some rest frame and saying, okay, beyond this we can't boost anymore. Right? So there's no Lorentz invariant regulator for this particular process if you want to make it. But I would say out of curiosity, this is not a major part of my story, but just how much should we really trust Lorentz invariance? Right? After all, these processes are exponentially suppressed. So do you really trust that the Lorentz symmetry is true to some incredibly arbitrary high boost? I don't know. And there's also like a much simpler regulator to cut off this divergence, which is that pretty much in any universe we live in, there's a space-time. The space-time, say, was created in a finite way. Either there's a finite size for it, or there's a finite time when the universe popped out of existence. Both of those are simple Lorentz-violating regulators of this thing, but no one would bat an eyelid about that. But anyway, that's just like my own particular comment about this. We don't have to have this problem if you simply are careful about what the UV is. So with that, let me actually talk about experimental signatures of this thing. This is still work in progress. I'm very interested in the story, trying to see what could actually come out of this. So the main problem, if you will, with the signatures of the story, the caveat, is that the formation time of this firewall, if it happens, is unclear. Right? You need to have an instant formation of this firewall in the inner horizon of the Reissner-Nordstrom black hole. Otherwise, GR does not solve the Cauchy horizon problem anymore. But whatever goes on in the interior of the Reissner-Nordstrom black hole is not visible outside. There's no visible signature outside. For a Schwarzschild black hole, it is plausible that you could wait for this firewall to form till the page time. That's when really something has to come out of the black hole and to solve the information problem. But I would say there's no particular reason not to expect instant formation. Right? That the moment the black hole is formed, there's no reason to think that this firewall couldn't just go out there, because it's going to break GR anyway. So if you're going to violate a law, why wait till you're old? Okay, violate it when you're young. It's more fun. So in the optimistic sense, I'm going to ask, well, okay, here's a solution in GR. There's a plausible formation story. Let me ask, what can I actually go and look at this particular thing? So one very interesting thing you can look for is like deviations from the no-hair theorem. Okay, both in general relativity and in electromagnetism. In GR, it's just a statement that this event horizon telescope will probe the geometry of Sagittarius A, okay, the black hole in the center of our galaxy, and basically ask, is it really the case that that geometry is well described by the Kerr metric? And of course, once your black hole or this firewall really exists, okay, the no-hair theorem goes out of the window because there's no horizon or anything over anymore. There's no particular problem sourcing a large energy density at the horizon itself. So this is experimentally something you could probe. And in electromagnetism, the question that interests me is that normally we don't think of black holes as having magnetic fields, because they're magnetic dipoles, there's no conserved quantity associated with them, so black holes should not have those. But indeed, if the firewall exists, the firewall itself could source the magnetic field. So one could ask, what is the biggest magnetic field a black hole could sensibly have, and is there something one could actually go and look for? Okay. This is something that's happened much more recently. This is not my work. This is work that was I think pushed by a bunch of people, Cardoso and company. And this is basically the idea that if you have a firewall or something out there, you could test for how a black hole rings down when it is formed, for example. So in LIGO, you've got these two black holes that are merging, and when they merge, they form a bigger black hole, and that black hole will ring down, and they have these quasi-normal modes that are going out there. And the idea is basically that for a relatively low angular momentum, there's an angular momentum barrier for these modes. Okay, and the standard story, of course, the gravitational waves that are produced by the ring down, the angular momentum barrier will just block them. And as they bounce back into the black hole is absorbing boundary conditions, so they just continue going inside the black hole, they don't get out. But if you actually have a firewall, you could in principle think about a reflection coefficient for the gravitational wave over there, because densities are Planckian, so who knows what. And if that is the case, you can think about there being essentially some kind of a cavity mode set up between the angular momentum barrier and the horizon there, and that could then give rise to this echo. Okay, the same signal appearing in there. There's an interesting story because this first thing came out, that's back in the day when I even thought about firewalls. I thought the whole thing was nuts. Probably still is nuts, I don't know. But there's an actual analysis of echoes by LIGO. Okay, and what is weird to me is that if you look at the LIGO paper, they will say that the evidence for this echo is that the null solution, so the null solution is that whatever signature they're seeing is simply noise, okay? That only fits the data with a p-value of 10 to the minus 2, 10 to the minus 2, sorry, 0.02, okay? So that's an anomalously low p-value, because you would think, come on, the null thing should really just be, the standard thing, right? So of course, this is not something to get super excited about. You can argue a lot about the specific statistics that was used into doing all these things. And obviously, if you have to argue about statistics to make any physical point, you don't know what you're talking about. All that's interesting is the fact that there's something that's testable potentially with advanced LIGO as sensitivities get better, because then you might be able to see a much weaker signal than otherwise. And it's also interesting to me to ask a question about the reflectivity of the horizon to just electromagnetic waves. These black holes, the Sagittarius A, for example, has stars orbiting it, and it could well be the case that light from the star hits the horizon and then bounces back, because I now have a non-zero reflectivity. Okay, so these are actually signatures that we are actively thinking about. So I'm well aware that I'm an illegal immigrant to the community of people who are allowed to solve the black hole information problem. Therefore, I'm going to commit a few acts of moral turpitude before I get deported. So here is the main interesting concepts. What is the main idea, right? The main idea here is that I have a large cancellation of positive energies by binding energy. That's what's basically happening. Okay, this big mass m squared over m Planck getting cancelled to enormous accuracy. We're familiar with this in particle physics. Okay, this shouldn't surprise us. So in particle physics, there's a composite axion. Okay, I have some big global symmetry. This global symmetry is broken at a very high scale f. And you know what happens? There's a massless Goldstone boson. You go inside this composite axion and you'll be confused. You would say, look, the fermions that make up this particular composite axion are at some very high scale. Its momentum is at the scale f. They could even be like massive fermions in there. There is like a flavor symmetry. Okay, but these enormous masses cancel incredibly accurately to give rise to a zero mass particle outside. And the reason why that physically happens, of course, is because the large mass is exactly cancelled by binding energy, negative binding energy. And there's a reason why that is true. The reason is because there's a light state that is guaranteed by symmetry. Okay? There's, of course, no symmetry reason that I've identified anyway for why such a miraculous cancellation needs to exist for these firewall solutions. If you notice, I didn't actually fine-tune the parameters. I simply said if R1 and R2 are order or something like this cancellation happens. I have no fucking clue why that is the case. Okay? So this makes me speculate that potentially there may be a new principle, okay, tied to causality in some way that causes this kind of cancellation. So such a cancellation is really required for the inner horizon of Reissner-Nordstrom and Kerr black holes. I've argued that such a cancellation does exist for the event horizon of the Schwarzschild black hole, although I don't know how we exactly form it. And there's a related problem, which I have not discussed, it's something identified by other people. Okay, this is not work due to me, which is that you can consider the rotating BTC black hole. It's just a two-dimensional rotating black hole. And you can ask the following question. This two-dimensional rotating black hole also has an inner horizon, outer horizon, all these kinds of things. And you can ask a very simple question, okay, which is, what do I need to do to regulate the vacuum energy in such a theory? So I just have some scalar field, okay, and I just write down this particular metric, and I'm going to compute the stress tensor, the renormalized stress tensor of the vacuum energy over there. And what you notice is that when you have the inner horizon, it turns out that the regulator for the vacuum energy has a problem. Okay? So if you try to regulate this vacuum energy just using a local counter term, it turns out that is not enough. You get new divergences in the story. Okay? So this is something work I think done by people over a number of years, but more recently by Eva Silverstein as well as Raman separately. Okay? And what that tells you again is this is a very common, simple solution, and all I'm doing is just taking this particular metric, and then I'm going to regulate the vacuum energy. And the moment I regulate the vacuum energy, I find out that the stress tensor suddenly has this big divergence at the inner horizon. Okay? There's some big energy density building up over there. So all of this somehow seems to me that anytime there is some funny business about causality, I'm finding this kind of solution, which is both required, right, in the case over here and here, where the solution is necessary, but I have no deep understanding for why they exist, other than just saying, well, it's kind of crazy that they do. I was kind of somewhat interested by the fact that I have believed many of these claims over here on the slide before, and it seems to me that the plausibility that the black hole information problem is not solved with a standard Hawking evaporation story does change quite a bit what I think about many aspects of quantum gravity. Some of the stories that I really believe. So for example, this kind of naked singularity that I talked about, this firewall solution, could well mean that black holes do not actually evaporate, right? Because the solution I gave you is just a naked singularity. There's no time dependence in the metric anymore. It's just a static solution. So maybe black holes don't actually evaporate, right? If this thing actually comes out there. And if that is the case, it may well be the fact that global symmetries are actually preserved under quantum gravity. I always thought black hole evaporation was the sharpest reason why you thought global symmetries could not exist. But, for example, a firewall could very easily carry the global symmetry out there, at which point there would be no particular reason to think that global symmetries are that unique compared to just local symmetries. Interestingly, it also weakens limits on things like new physics that we've often placed, even I've often placed, based on black hole evaporation. For example, primordial black hole dark matter, we ruled that out by talking about Hawking evaporation when they're light enough. But if that is not the case, maybe you should look for primordial black hole dark matter below 10 to the 16 grams. I think that's something that's interesting to me now. Even LHC limits on extra dimensions are often placed based upon assuming that the black hole evaporates in the Hawking process. So I don't particularly see any compelling reason to think that is the actual way it happens. People like Mina Armanitaki have used black hole superradiance as a way to place limits on particles like axions. And even that is something that's subject to this, because if the black hole has hair, okay, if it's not exactly just a rotating Kerr solution, you could source higher dimension. Sorry, you could source hair. Like you could basically have higher order multiple moments in the metric, and those could actually mix the growth of superradiant modes, completely damping them out. So there's no particular. So it seems to me that these kinds of bounds that are placed on light fields through claimed observations of black hole rotation are actually subject to some sort of theoretical uncertainty, in my view, given that we don't actually understand how black holes in fact evaporate. And I'm actually very curious to fully understand the gauge theory analog, if you will, of the firewall solutions, right? Whether you believe my formations argument or not, you can't really argue with the fact that the solution exists, okay? And if the solution exists, it is somehow this crazy statement that there is this big cancellation of positive and negative energies, and maybe something like that could also be used as a new solution to the hierarchy problem, where in fact there are no obvious symmetries why that exists. So to basically wrap up, I would say even black holes have firewalls. Thank you. Yeah.
So GR oftentimes is concerned with the stability of the solution.
Yeah.
Do you have anything to say about whether or not these shell solutions that you're proposing can survive under that small perturbation?
Yeah. So basically, I'd have to know what the shell is made out of to make that argument.
No.
You do.
No.
Of course you do.
You've written it as a classic GR solution
Yeah.
with the Israel junction conditions.
Yeah.
You can look at that solution and analyze its behavior under...
No, but he's basically asking if I perturb the shell a little bit, make a sound wave or whatever, how does it behave, right?
No, if you perturb the outside metric, you have a solution of general relativity.
Yeah.
You can look at the field equations for a perturbation of that solution.
You can look at the external perturbations, I agree, right? But not the shell itself, because it depends upon what the shell is made out of.
But even that you can probably model simply if you take it,
You could.
I think what he's talking about is the equational state of the perturbation,
Yes.
which might not be the same as the equational state for the background.
Correct.
Namely, the relation between P and rho and dP by d rho. But even if I give you that, you can model it very simply. That is what's called speed of sound in cosmology.
Yeah.
It's that extra one partial derivative, but
It's something to be done. It's just that you need that extra information. That's all.
But
We have not
I
done
think
it.
what you really need to do is to show that this thing is generically very long-lived in
Sure.
order to simulate a black hole.
Sure. Yeah.
I may be remembering wrong, but I thought there was somebody's theorem, and I know that this is it's in Weinberg's book, GR book, for example, where that answered a question very much like what you're saying. That they ask, how much can a star look like a black hole? So
Yeah.
specifically, how close can the outer boundary of a star be to the horizon? And they assumed something about the energy conditions, and I think something about the equations of state. So the assumptions I'm not remembering, but the result was that there's you get some sort of an interesting factor like 7/5 or something. 9/8. Thank you.
9/8,
Okay,
yeah.
so I'm just wondering, this thing seems to. Do they require too strong an energy condition? Or
No,
what's
it's basically the
relationship
fact that
of what you're
their condition
trying
is
to do?
just the fact that they are, for example, requiring that things are non-singular, and I'm just.
So you're claiming that this solution can be approached by a set of non-singular solutions,
Right.
As you.
As I go towards, exactly, yeah.
So-
But I still have a singularity in the core.
So before you get to M Planck,
No, I always have a singularity in the core.
yeah, I don't think they're. So that's the difference.
That's the
those
difference, yeah.
solutions.
Yeah.
I don't think. I mean,
No,
that would be
this is-
surprising.
No, because like
Because the bound is independent of what happens inside.
No, the thing is what happens is basically when you say what goes wrong as you make the star more and more dense or more and more compact, physically what you see is that the pressure of the core blows up. That's what you actually show. Okay? And in this case, that's always true. Yeah.
So I think you mentioned that none of this was particularly sensitive to cosmological constant.
Yes,
So you could run all this in ADS.
you could.
So there's some work in ADS3 in trying to construct, these little shells that would, have you thought about
No.
what kind of
No, we've not.
operators you would need in the boundary to try and...
Not really. No, we haven't done that. I think it's an interesting thing to do. So in a sense, for me, I would say this is an example of something where knowledge of the UV is important. So if you think you have some ideas of what the UV could be, maybe you should try it to see what actually makes sense. Yes, sir.
So a comment and two comments and a question, I guess. First comment is that the question that you began with, the issue of the stability of the Cauchy horizon.
Yeah.
That's what's called the strong cosmic censorship hypothesis. And there is an enormous amount of work in the literature about whether Cauchy horizons are stable under small perturbations.
Yeah.
And while it's not completely settled for Reissner-Nordstrom, there is extremely strong evidence that Cauchy horizons are not stable, and that in just standard GR, a small external perturbation gives you a light-like singularity about the Cauchy.
So I'm not disagreeing with that statement.
Okay.
I'm just disagreeing with the statement that it's a small external perturbation in the sense that you'd have to regulate whatever divergence you're getting, and you will find that when you cut off that divergence at a sub-Planckian distance, okay, that you don't know how things actually move, you realize it is not such a small perturbation. It's not too big, but it's something to order the mass of the black hole.
No, the statement is that there is no open set of solutions around.
Yeah, but that's only because you trust your metric.
That means that there are, that if you have an arbitrarily small perturbation,
Yeah, that's just not
that
physically.
you get a light-like singularity. Arbitrarily small.
Yeah.
So
That
you
is what they
take-
say,
yeah.
but it doesn't make sense, right? Because if you think about it,
Of course.
no, it doesn't. It's only because you believe the metric to R equal to R1 to extraordinary precision. Think about it. I have a real solar mass black hole out there. I'm not going to be able to put a tiny 10 to the minus 25 eV photon outside. That is not going to go in there and change the singularity from being what it is to something light-like, right? So I agree with what you're saying. This is what the mathematics would show. And that's only because you take R equal to R1 and say it is actually an infinity. And what I'm saying is that I don't trust GR enough at the level of R equal to R1 exactly. I'm going to regulate that divergence. Once I regulate it, there is a finite but much bigger mass that you need to make that divergence go away. To create that divergence. Sorry.
Yeah,
No, that's just you can just see that, okay?
yeah, so you're looking at time-like singularities rather than light-like,
Yeah.
and I suspect you get very different results if you look at light-like singularities.
I doubt it, right? Because
How do you regulate distance from a light-like singularity?
I mean, it's sort of more of a physical statement to me that basically you still have to hit that surface, right? You still have to go through that particular area in order to do anything, and you have to trust GR to extraordinary accuracy to do that.
No, well, this is a basic problem that this idea of a Planck distance away only makes sense in a static solution.
Sure.
Because how do you measure a distance along a null geodesic, physical distance along null geodesic is zero.
That's only because you trust GR to extraordinary accuracy, right? That's all. So
Well,
basically,
no,
one would say that
any theory that has a Lorentzian structure in it, there are going to be some geodesics along the distance.
yeah, but it's like you have to know the motion along that distance tremendously accurately. Anyway, look, I don't want to argue about this too much, okay? In the sense that whatever, yeah. And in fact, more recent work has even shown that in the case of the Kerr black hole, they've actually, this is by Andras Vasi and company, I believe, who have actually shown that in the Kerr black hole, the Cauchy horizon is in fact just C0 discontinuous. So in principle, you're able to continue going in there. And there's a category of people who worry that now the Cauchy problem exists in general relativity.
Yeah.
So
Fermos and
exactly. So even with the external perturbation story, it is still the case that the recent work has shown there's a Cauchy problem.
Yeah. That's Kerr, though, not Reissner-Nordstrom.
That's Kerr, yes. And for Reissner-Nordstrom, I believe it's Peter Heinz and company who showed that when you have a positive cosmological constant, this divergence goes away again. Which again, to me, right, physically is suspicious that a positive CC should change some story about your interior.
Okay, so let me ask my question.
Yeah.
In your picture of the whatever it is that's involved in the formation of this singularity, what you've been working in an exactly spherically symmetric model.
Yeah.
And typically, you don't expect exact spherical symmetry. How do you get a mechanism that allows this singularity to form singular shell to form simultaneously at points that are space-like separated from each other? How does this side of the black hole know that it should form the singular shell at the same time that this side?
So so the precise point is the fact that I would think that the singularity forms, the shell even forms only after the collapsing matter has already reached a Planckian density. Okay, so that's my picture. So at that point, once this is just some Planckian object that's already in there, an object at Planckian density, right? So this is a very much a lawyer-esque statement. Like I can't tell you what the theory is, but I don't know what the theory is. All I can tell you is a plausibility argument. Okay, I have like a get out of jail kind of card where I basically say, okay, I've formed this Planck mass object, this Planck density object, and then there's dynamics in that Planck density object that cause things to move outward. Much like how if I take, let's say, a standard supernova style explosion, right? What happens is that there's some stuff collapsing, there's an object that forms in the center that gets to neutron star densities, and then stuff goes outward, right? This happens all the time in the real world. I'm just arguing for why something very similar is plausibly true in the black hole as well.
Okay, that'll make a huge difference in the quasi-local modes then.
I could,
I
yes.
mean, apart from boundary conditions, if you have this matter
Yeah,
moving out.
absolutely.
and stopping, you're
Absolutely,
going to get
absolutely,
ring
absolutely.
down modes.
Absolutely, yeah. Yeah, so as and when those ring down modes are measured at the appropriate frequencies, I think that is another independent test. So in a sense, you could just ask how well you know those frequencies. Absolutely.
Okay.
Yeah.
Okay, let's thank Surjeet again.
Thank you.